Hello everyone, my name is Haicheng Liu, a PhD student from the University of North Carolina at Charlotte. My advisor is Dr. Teifu Zhao. Our project is modular hybrid silicon carbide and silicon-based battery inverter for energy storage integration. We started this project from July 2019. The first thing I will introduce is our motivation for doing the hybrid switch. The wide bandgap devices such as the silicon carbide MOSFET has many superior characteristics. It has higher operation voltage, higher working temperature, and lower switching loss. Well, the biggest disadvantage is the device cost, which is much higher than the silicon devices. In order to combine the advantage of silicon carbide and silicon devices, the silicon carbide MOSFET and silicon IGBT hybrid switch is proposed. The configuration of the hybrid switch is shown here. A small silicon carbide MOSFET is connected in parallel with a large silicon IGBT. In every switching period, the silicon carbide MOSFET is turned on first and turned off last to realize the silicon IGBT zero voltage switching. Thus, the switching loss can be reduced. Since only small silicon carbide MOSFET is needed, the device cost is also reduced. So by using the hybrid switch, the inverter can increase its power density and switching frequency while maintaining a low system cost. The objective of our project is to develop an inverter for the energy storage integration with a DC voltage up to 1500 volts. In order to realize the high power density with lowest system cost, we proposed the hybrid switch-based AMPC inverter. In this topology, we use the silicon IGBT as the 4 internal active switches. Hybrid switches are used for the other 2 switches. The modulation method is shown here. Only the hybrid switch will produce the switching loss. In this topology, the voltage stress of all the power devices is only half of the DC voltage. So the 1200 volts silicon IGBT and the silicon carbide MOSFET can be utilized in the 1500 volts DC voltage application. Also, the silicon carbide and the silicon hybrid switch can also provide the system with high efficiency and high power density with a relatively low system cost. We did the simulation in Plex to validate the efficiency improvement by the hybrid switch. The simulation results and simulation conditions are shown here. The right line is the efficiency curve of hybrid switch-based inverter. The black line is the silicon IGBT-based inverter efficiency. It is noted that the efficiency of hybrid switch-based inverter is overall higher than the pure silicon IGBT-based inverter. The maximum inverter efficiency improvement is 1.75 at light load condition. Apart from the proposed hybrid switch-based AMPC topology, we have also made many progress. First, we made the power device optimization. S1 and S5 as shown in the circle, we used the half-bridge module from the Infineon, and for the hybrid switch, we used the discrete power devices. We also made a current ratio optimization method for the hybrid switch. Here, the current ratio we use is 3:1. After this, the power block, including the power devices and heatsink, are designed. We also use the Plex to validate our design. The simulation results show that the maximum junction temperature of all the power devices are all under their limitation. Our inverter packaging is shown here. In this design, the power density can reach as high as 45.4 watt per cubic inch. This is believed to be a very high value among the 1500 volts DC voltage battery inverters. Up to now, we have tested the gate driver circuit and we are doing the inverter implementation in our lab. In the end, I want to thanks for the support from Power American and LS Energy Solution. That's all my presentation. Thank you for watching.